Okay, so hi everyone, welcome back to yet another video. So today in this video we will be discussing this problem on Codeforces, that is non-academic problem, and this problem has appeared recently in Div 3 contest 954, and this problem is rated 1900, and multiple concepts related to graph theory like finding and detecting bridges in graph, and also a little mixture of dynamic programming on trees that we just used in the previous video, so we will use that here also. So let us get started with this problem. So the problem reads like this, that we are given a connected undirected graph and the vertices are numbered from 1 to n. So our task is to minimize the number of pairs of vertices. Obviously they will lie between 1 to n, between which there exists a path in this graph. So to achieve this, you can remove exactly one edge from the graph, and then we have to find the smallest number of pairs of vertices. So I will explain you very soon in the blackboard what does this mean. So the input for this problem first requires the number of test cases, and then the next line contains two integers n and m representing the number of vertices in this graph and the total number of edges in this graph, and the next m lines contains two integers u and v, indicating that there is an undirected edge in the graph. So this graph is an undirected one, so there will be an edge between both u and v, right? And it is guaranteed that the given graph is connected and without multiple edges. So the given graph is not disconnected, it is just a single component, right? And it is guaranteed that the sum of n and the sum of m over all sets of inputs will not exceed 2 into 10 to the power 5. And for each of the test case we have to output just one integer, and that integer will represent the smallest number of pairs of reachable vertices if exactly one edge is removed from this graph. So this is the problem. Let me now take some examples and explain you on the blackboard how does these outputs are coming for these test cases. So let us now discuss these examples one by one. So let us now discuss the very first example given in the problem. So in this example there are two vertices and therefore one edge between them, right? So in the question it is said that we are allowed to remove at most one edge from the graph, and after removing that edge what we want is we want to reduce the total number of pairs of vertices which are reachable from each other. So see here, initially since there is a edge between 1 and 2, so and it is a bidirectional edge, right? So it means that we can go from 1 to 2 and we can also go from 2 to 1. So we can say that 1 comma 2 is forming a pair of vertices, right? A pair of vertices which are reachable from each other, right? So this is one pair, and since in the question it is allowed that I can remove an edge and at most one edge between any two vertices, right? And since there here is only one edge present, so suppose I remove it. So let's see what happened. So now I have removed the edge, and as now you can see I cannot go from this 1 to 2 anymore, and similarly from this 2 I cannot come back to 1 anymore, right? So it means that initially we were getting one pair, right? But now since we will not be able to go from any node to any other node, so we can say now we don't have any pair of vertices, because this 1 comma 2 represented what? It represented that we can go from 1 to 2 or from 2 to 1, right? But since here it is not possible to go from any vertex to any other vertices, so that's why here is no pair. So the total number of pairs that we got here now is 0, and we wanted the minimum of it. So as you can see, when we removed this edge we got 0, that is 0 pairs of vertices which will be reachable from each other after removing at most one edge from the graph. So for this test case, that's why the output is 0 in the example. Now look at the second example given in the problem statement. So in this example we have 3 vertices and 3 edges between them. So now if you see, then initially when all the edges are present, then we can go from 1 to 2, that is we can go from 1 to 2, right? Similarly we can go from 1 to 3, right? Similarly we can go from 2 to 3, right? So it means that initially it is possible to go from every vertex to every other vertex, because since the road is bidirectional, so we can go from any other vertex to any other vertex, because this whole thing is connected. So if I write here, so we can go from 1 to 2, right? Similarly we can go from 2 to 1 also. Similarly we can go from 1 to 3, and thereby we can also go from 1 to 3 to 1, and also we can go from 2 to 3, and similarly we can go from 3 to 2. So we will not consider these two things different, right? So if we are able to go from 1 to 2, then I will treat the same for it as 2 to 1, right? So this will form one pair, this will form another one pair, and this will form another one pair. So initially when everything was connected, we were getting a total of 3 pairs of vertices which were reachable from each other. But now, since the question has given me the liberty to remove any one at most edge, so suppose I decided to remove this edge, that is the edge present between 1 and 2, this edge. So what will happen when I will remove this edge? See, so now I have removed this edge, right? So let us now again calculate the total pairs of vertices which are reachable from each other. So now as you can see that if I try to go from 1 to 2 again as I did before, I will not be able to go from this path because this path does not exist anymore, right? But still if I try to go from 1 to 3 and then from 3 to 2, then I will be able to go from 1 to 2, right? So it means that still we can go from 1 to 2 and thereby from 2 to 1 by using this path, right? So that's why this is forming a one pair. Similarly, if I try to go from 1 to 3, then I can still go from this path because this path is still connected and not removed. So that's why 1 to 3 is still reachable and thereby 3 to 1. So I can say that this is contributing to another pair. And similarly, if I try to go from 2 to 3, that is this, right? So this is also still connected. So I can go from 2 to 3 or from 3 to 2. So again, one pair. And thereby on summing this up, it is still giving us 3 total pairs. So you saw that when I removed this edge between 1 to 2, nothing changed. That is, the total number of pairs of vertices which were reachable from each other earlier when everything was connected is same now, right? So it means that on removing this edge, we were not able to minimize our answer. So we will not remove this edge, right? Because it is not giving us less number of pairs, right? Let us now try to remove this edge and see what happens. So now I have removed the edge between 2 to 3, and again you can see very clearly that even after removing this edge, I will still be able to go from 1 to 2 via this path and thereby from 2 to 1. Similarly, I will also be able to go from 1 to 3 via this path and also from 3 to 1. And similarly, I will also be able to go from 2 to 1 and then 1 to 3, thereby 2 to 3 and thereby 3 to 2, right? So it means that still the graph will be reachable completely when I removed this edge, right? So again, when I removed this edge, I will still be getting my output as 3, right? And now let us give our last try to remove this edge and see what happens. So again, if you see, then clearly we can go from 1 to 2 and then from 2 to 1. Similarly, we can go from 1 to 2 and then from 2 to 3, thereby 1 to 3, and similarly from 3 to 1. And similarly, we can also go from 2 to 3 and thereby 3 to 1, 3 to 2, right? So it means that no matter what edge you remove in this graph, you will still be able to reach every vertex from every other vertex. And that's why your answer will not change at all in every case, right? That's why the output for this example is 3 only. Let us now discuss this example, which is the third example. So the output for this expected is 4, right? Initially, what is the total number of pairs of vertices that is reachable from each other? If I tell you that the whole graph is connected and is bidirectional, doesn't it mean that we can reach any vertex from any other vertex, right? And it is mentioned in the question that the whole graph will always be connected and will also be bidirectional every time, right? Since the graph will be connected and bidirectional every time, it means that we will be able to go from every vertex to every other vertex. Since there are 5 vertices, so let me write down here. So 1 2 3 4 5. So it means that I can go from 1 to 2. Similarly, it means that I can go from 1 to 3. Similarly, it means that I can go from 1 to 4, and thereby we can go from 1 to 5. Similarly, it means that we can go from 2 to 3, and then from 2 to 4, and then from 2 to 5. Similarly, we can go from 3 to 4, 3 to 5, and finally from 4 to 5. And why this is true? Because the whole graph is connected and is bidirectional, as you can see. So it is possible to reach every vertex from every other vertex, right? So it is also, you can consider it like a strongly connected component, because it is possible to reach every vertex from every other vertex. Now the question is how you will calculate the total number of such pairs, like 1 2 1 3 1 4 1 5, then 2 3 2 4 2 5, and then 3 4 3 5, and finally 4 5. So just use this formula, that is n into n minus 1 divided by 2. Since the value of n here is 5, so 5 into 5 minus 1, that is 4, divided by 2, so it will give you 10. And if you start counting the total number of pairs that I just told you, so it will be 10 only. See, first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, and then 10th. So the total number of pairs possible when everything is connected will be equal to n into n minus 1 divided by 2. Keep this formula in your mind, it will be used later, right? So let us now continue on this example and see why the output was 4. We now know very well that whenever we want to calculate the total number of pairs, it will be equal to n into n minus 1 by 2 only, right? Okay. Since we can remove one edge from the given graph, so suppose I removed the edge present between 1 to 2, and also if you remember, then the total number of pairs reachable from each other before was 10 only, right? So now let's see what are the total number of pairs present now that are reachable from each other in this current graph. So since I have disconnected the edge between 1 to 2, it means that it is not possible to go from this component to this component anymore, and vice versa, right? So now if you start to calculate again, then you will notice that from 2 we cannot go anywhere, but still we can go from 1 to 3, or from 1 to 4, or from 1 to 5, or from 3 to 4, or from 3 to 5, or from 4 to 5, right? So let me write that down here. So how many pairs we are getting in total now? So we are getting one pair from here, one here, one here, one here, one here, one here. So we are getting a total of 6 pairs, right? So now if you see, then after removing this edge, we are getting a total of 6 pairs. But before, when everything was connected, we were getting a total of 10 pairs. So it means that we have successfully reduced the total number of pairs of vertices that are reachable from each other by removing this edge. So now we have a better answer, which is 6, when we removed the edge present between 1 to 2. Now let us try to remove the edge present between 1 to 3. So if I remove this edge and calculate again, now as you can see that on removing the edge present between vertex 1 and vertex 3, I am getting a total of 4 pairs now, which is obviously less than 6, right? So now I have got a better answer than before. So the minimum that I have got till now is 4. And if you go on trying by removing each of the edge, that is this one first, then this one first, then this one first, and calculating the same thing that I just did for these 2 edges, then you will realize that it is the minimum that we can get by removing any one edge, right? So that's why for this example the output is 4. So by now I hope you have understood what does the problem is asking clearly, and how the outputs will be coming for each of the given graphs. So let us now see what are the concepts that we will be using in this problem in order to get our correct output. So before coming to the main thing, let us first discuss some of the basic things. Let us now discuss these 3 terms first. The first is bridge. So what is a bridge? So bridge is nothing but one of the edge in the given graph, upon removal which the total number of components increases by 1. So what does that mean? Let me explain you with an example very quickly, so it is not a very hard thing. See, so initially the total number of components present in this graph is 1 because everything is connected, right? Suppose I decide to remove any one of the edge, let's say this. So what happen if I remove this edge? So as you can see, still the total number of components is 1 only. Similarly, if I have decided to remove this edge, then again the whole graph is connected, right? But now if I remove this edge, then you can see clearly that now the graph is divided in 2 different components. That is, the number of components is now increased by 1, that is 2. That is the first component and the second component. So it means that this edge is a bridge because when we removed it, the total number of components increased by 1. Similarly, if I try to remove this edge, then again the total number of components increased by 1, right? So it means that this edge, that is this one, is also a bridge, and similarly this one is also a bridge. So in this graph there are total of 3 bridges, right? What do you mean by a span edge and a back edge? Let's see. So let us now consider this example in order to understand the span edge. So what do you mean by span edge? So suppose the tree was rooted initially at this vertex. So if it was rooted at this vertex and we would have tried to draw the spanning tree for this graph, then this edge, this edge, this edge, this edge, and this edge would have been a part of that, right? So we can say that these edges are nothing but span edges, right? Because they are forming a member of spanning tree. So this edge is nothing but a back edge, and the remaining edges are span edge for this graph, right? So what does this back edge is doing if you see clearly? So it is doing nothing but it is connecting itself with its own ancestor, right? Because if the if this graph was rooted at this vertex, right, so would have gone from one, so we would have gone from this vertex to this vertex, then this vertex, then this vertex. So that's why we can say that this vertex is nothing but an ancestor for this vertex. So this back edge is connecting this vertex with its own ancestor. So we can say that this is a back edge because it is connected to a member which has been previously visited when we have started our DFS call from this route. So now we have understood the meaning of bridge, span edge and back edge in very simple terms, right? So how we will use the concept of these bridges and back edges in order to solve this problem? So see, the problem has asked us to minimize the total number of pairs of vertices that are reachable from each other by removing at most one edge from the graph. So the question is, we can remove any one of the edge, right? We can have either removed this edge, this edge, this edge, this edge, this edge. But how we will decide that which edge we should remove in order to minimize our answer? We will say that we will not arbitrarily remove any edge and check one by one, right? Obviously you can do one thing, that you can remove one by one and check every time, but that brute force will not make any sense here because the constraints are high. So that's why what we will do is, instead we will try to remove such a edge will increase our chances of minimizing our answer. So if you remember, then for this example we got our answer as 4, right? And we got this when we removed this edge. And I just explained you the meaning of bridge, that is such a edge that will increase the number of components by 1 when removed from that graph. And here also if you see, then this is nothing but a bridge only, because if I have removed this edge from the graph, then the total number of components would have increased by 1, right? So that's why I can say that this edge is a bridge. And why is it always feasible to remove bridge only in every example? Because on removing a bridge, the total number of components are increasing, right? But since now I have removed the bridge, so it means that I cannot go from 1 to 3 or 4 or 5 anymore, right? And similarly from 2 to 3, 2 to 4, 2 to 5 anymore. So that's why it is always feasible to remove only the bridge and not any unnecessary edge. Because if you have removed some other edge, then still the everything would have been remained connected in this example at least, and that's why our output would have not decreased much. So I hope you got the concept why we will only try to remove bridge and not any other edge, right? So now if I tell you mathematically here, then earlier if I was able to have a total of 10 pairs, and after removing this bridge, how many pairs we have lost? We have lost a total of 6 pairs. How? From 1 to 3 we are not able to go, 1 to 4 and 1 to 5. Similarly 2 to 3, 2 to 4, 2 to 5. That is a total of 6 pairs. And what are these 6? And what is this 6? It is nothing but the total number of elements present in this component into the total number of elements present in this component, right? That is 2 into 3, that is 6. So 2 into 3, so I can say 10 minus 6, that is 4. And this is what the expected output for this problem is. So the first key concept that we understood till now is that if we have the liberty to remove any edge, we will always try to remove the bridge only, right? Because it will increase the total number of components and thereby the total number of pairs that will not be able to reach from each other anymore. But if you have noticed, then in this example, there was only one bridge. So if I redraw the graph initially, what was before? So the graph was initially something like this, right? And we had only one bridge in this example. So it was very easy to understand. But suppose the same graph had multiple bridges. So it means that whenever we will be having multiple bridges in the problem or the example, then we will be always checking the total number of pairs that we have lost while removing that bridge, right? And thereby minimizing our answer every time. So I will very soon explain you how we will do this, right? So the second thing that we understood now is whenever multiple bridges will be present in an example, then we will have to check for all of those bridges and thereby minimizing and maximizing our answer whatever required every time. So you now must be wondering how for every example we will detect this bridge. So if you know, then there exist many algorithms to detect a bridge, like Tarjan's algorithm and classical method of finding the bridge, right? But I believe that these methods are confusing and not much intuitive. So is there a better method or any other method which is more intuitive and meaningful, which will help us to detect a bridge and also print that bridge, right? So yes, there exists a method, and this method has been discussed extensively in one of the Codeforces blog. Let me show you that. So if you have read this blog by Is This FFT, then this blog is about tree DFS and its applications, and by performing a DFS on tree, find bridges or articulation points using this method. And as you can see, everything was given here in detail, right? So I'll explain you very soon how this method works in order to find a bridge, and we can also print that bridge, right? So suppose now you have learned that method and now you have detected that bridge. That is, the bridge that you have now in your hand is 1 2 3. And one more thing, if you have noticed, then when I drew this graph, then I drew it such that 1 was present on the top. That is, I treated 1 as the root vertex for this graph. So suppose I start a DFS call from 1, then what will happen is that the DFS call will go from 1 to 2, and then from 2 to 1, then from 1 to 3, then from 3 to 4, then from 4 to 5, then from 5 it will not go anywhere, then again come back to 4, then to 3 and to 1 and will get end, right? If I try to mark their levels, so this is present at the top because this is the root vertex, right? So let me say that its level is 1. Similarly, these childs of 1 have a level 2. Similarly, the level of this child of 3 has a level of 3, and similarly this 5 has a level 4. So I was telling that suppose you have now detected this bridge, right? You have detected this bridge, that is 1 to 3, and now you want to remove it. So just imagine, or you can try to write it in a paper also, but I will show you here. So what will happen when I will remove this 1 to 3 link? So this will be another component and this will be another component, right? So clearly you can see that this bridge when present between these two vertices, so clearly since this is the parent of 3 and 3 is the child of 1, so they have different levels, right? That is, 1 has a level of 1 and 3 has a level of 2. So now I have removed this bridge as I told you, and now since the graph is divided in two different components, then what I told you earlier is simple, that I will simply multiply the total number of elements present in this component by the total number of elements present in this component, because that would give us the total number of pairs that we are able to use earlier but not now. That is, these number of pairs are now lost. So what is the total number of pairs here? So it is equal to 2 into 3, that is 6. So 6 such pairs are lost now. That is, we cannot use them anymore in our answer, right? So the key take is how we will find that in this component the total number of nodes is 2 and in this component the total number of nodes is 3. So for now just assume that you have learned that technique and is knowing how to find a bridge as of now. Hold on with me for a few more minutes. I want to calculate the total number of elements present in this and this respectively, right? So what we wanted is the total number of elements present in this component. So if you are able to see, then what is this? These are nothing but the total size of this subtree rooted at this vertex, right? So if this tree is rooted at vertex 3, then it will have 3 elements only, right? 3, 4 and 5. So this value that we wanted, that is the total number of elements present in this component, will be nothing but the subtree size of this one end of the bridge, right? Similarly, what is this 2? It is nothing but the subtree size rooted at this end of the bridge, right? So this was the bridge earlier, so it has two ends, 1 and 3. Since we have removed the bridge, so for now it will be like the subtree size of 1 is 2 and the subtree size of 3 is 3. So when we multiply them, 2 into 3, we get 6. And initially the total number of possible combination was 4, and now we have lost 6 combinations, so the remaining one is 4, and that's why our answer was 4. That in order to calculate the subtree size, what we do? We apply dynamic programming on trees concept, right? And by the way, if you have watched my previous video, then I have discussed the same thing here, because the same thing was used there also, right? And there is a dedicated question for this on CSCS problem set, so let me show you that. So this is the problem in the CSCS. So in this question we are asked to find the subtree size -1. So we don't have to include the current node size, right? So it's the same thing, right? So if I show you up the code, then see. So I have discussed the exactly same thing in my previous video, so if you have not watched, you can watch it. But if you know it, and if you know it beforehand, then it is also a very good thing, right? So what we do in this basically is we start a DFS call from 1, that is we treat 1 as the root vertex of the tree. And you know how to do a DFS on a tree, like we do not use any visited array, we just take a parent and see if it is if the child is not equal to parent, then we again do a DFS call until we reach to the leaf node and simply combine the result of all of the child nodes back to the current node continuously. And also for each leaf node we set the subtree size equal to 1, because it consists of itself only, right? And also for all other nodes also it consists of 1 at least, that's why we set the subtree size for each node equal to 1. And in this way the count array finally gives us the subtree size for every element present between 1 to n, right? So this is not a very hard concept, and this comes under DP on trees only, right? And now one last thing I think I should tell you, because just now I told you that if on applying that same logic we will be able to find the subtree size for every node in the given original graph, right? But that thing was applicable only when the given graph is tree. But here, and what is the definition of tree? And moreover, this was the original example, right? So what is a tree? So you know very well now, at least I hope so, that a tree is nothing but a graph that consists of n vertices and n-1 edges with no cycles. So cycles should not be present. But here clearly you can see that from 3 to 4, 4 to 5, and then again from 5 to 3, this is a cycle. So if we try to calculate the same array here using that calculation logic that I just told you for the CSCS problem or in the previous video, then it will not work. Why? Because this is not a tree. In order to work for it, we have to think like this edge does not exist, and then only it will give us the correct result. So I hope you have understood what I wanted to tell here, and it is easy to understand, it is not a very hard thing, right? So that's why whenever we will be finding the subtree size for the given graph, we would be only finding it for the graph that does not consist of any loops or edges that form a cycle, and we want it completely to be act as a tree only. So suppose somehow I have converted this graph or made a copy of this graph into something like this, in which there is no back edge present anymore. And if we apply the same DP on tree logic here in order to combine the result for the child on each node every time till the end of our DFS call, then we will get the correct subtree size, isn't it? So the subtree size will look like, so I can say for 1 it would be 5 only, for 2 it will be itself, and also yeah, I'm not considering this, so you can forget this as of now, and for 3 it would be 3 only, and for 4 it would be 2, and for 5 it would be itself, that is a leaf node. So this is the subtree size array that we will get. Since we knew that 1 to 3 is a bridge, and I told you that initially we had a total count of 10 possible pairs, and since the question has asked us to minimize this, So when we would have come to 3 from 1, then the level was increased by 1, right? Because initially the level was 1 and we are traversing to one of its child, that's why the level increased by 1 for every step we went down. So this level would help us in understand that for a given pair of grids, what is u and what is v. So suppose in the whatever data structure we will use to store every bridge, right? So the first element would be treated as u and the second would be treated as v, right? U and v. So it is possible that when we were storing our bridge, the level of u would have been more than that the level of v, or rather the level of v was more than that of the level of u, right? So here if you see, then this is our u and this is our v, right? And the level of 3 is more, that is the level of v is more than that of the level of u. And since we wanted to calculate the subtree size for this, so this will be nothing. So it means that the whatever node of the bridge, that is 1 or 3, level is more, so for that the subtree size will be right in this array already. So since for 3 here it is 3, so you can see that the total number of elements present in subtree is 3 only. And this is true for what node of the bridge? It is true for that node of the bridge which has a more level than the other node of that same bridge, right? So that's why this leveling turned out to be useful here. And now we want to find the right value for 1, because for 1 the whole subtree here is consisting of 5 elements, but we know now that when we have removed this, it only consists of this much elements, that is 2 elements, right? And if you try to look one last time, then you will realize that this thing that we want is nothing but the total subtree size rooted at this vertex, that is this, minus the subtree size rooted at this 5 minus 3, which is 2, and which is equal to this only, right? So in this way we will be calculating the subtree sizes for both of the ends of this bridge and will be multiplying them, and whatever value will be coming, it means that we have lost this much number of pairs, so we'll be subtracting that from the original one, and for that whatever answer will be coming, we have to minimize that. So I hope you now have understood completely what I want to tell, and I also told you that later I will be telling you how we will find bridge in the given graph. So let's discuss that now. So consider this example in order to understand how we will find the bridge using the technique discussed in the blog. So in the blog it is written that we will define a DP state for each of the vertex present in this graph. So suppose we have a vertex u, right? So for that we will define a DP state, and what does this DP state will represent? So it will represent the total number of back edges that will connect u's descendant including itself to u's ancestors. So what does this mean? Let me explain you very quickly with this example. So suppose we have this as our u here and this is our parent of u, right? So as you can see that we want to define a DP state for this u, that is DP of 3, and I have also explained you what does a back edge mean. Back edge is nothing but a node that connect with its ancestor. So here as you can see in the given example, this is a back edge, right? Because it is connecting 4 to one of its ancestor, that is 2. So this is a back edge clearly. So how we will calculate this total number of back edges that will be present between the u's descendants, that is this part, to the u's ancestors, that is this part, right? So this DP of u will be equal to total number of, so this hash will represent total number, so total number of back edges up from u, right? So a back edge that will be connecting u or originating from u and is going upwards, plus back edges going downwards from u, right? Going downwards from u, minus the summation of this DP state for each one of its child. So this is the DP state that we will define for each of the vertex, and it will represent the total number of back edges that will cover the descendants with the ancestors of that node. Why we are treating these two things as plus and this as minus? Because what does this DP state represent, if you remember? So this DP state represent the total number of back edges that will be connecting u and p somehow, right? So if a back edge is connecting this u to some of its ancestor, then it means that clearly u and p will always remain connected if this edge is removed, right? So that's why we are adding this to our answer, or the DP state rather, And why we are subtracting the back edges going down from the same u? Because suppose a back edge would have remained connected from 3 to some vertex. So if we remove this vertex, this edge between the u and its parent, then this back edge will have no contribution in order to connect this u and p, right? Because earlier we saw that when we removed this edge, because of this back edge, we were be able to go from 3 to 1 and then 1 to 2 because of this back edge, right? Which was going upwards from you. That's why we were treating it as plus. And since this it has no contribution in increasing the chances of connecting with p back, so that's why we are giving it a sign of minus. And also we will be adding the results of all the children. Why? Because it is clearly visible here in this example that 4 is the child of 3, that is u, and it has a back edge, right? So this back edge is connecting this children to the parent, right? And if we have removed this edge, right, so still we would be able to go from 2 to 4 and then from 4 to 3. So we were able to reach from 2 to 3 through this back edge, right? But if this back edge was not present and we would have removed this edge, then we would not be able to go from 2 to 3 or 3 to 2, right? That is, it was a bridge in this case, right? So that's why this is helping us in order to connect u or reach u from p or from p to u via this back edge, which is originating from the child of u, right? So that's why this positive sign for every children. And ultimately, if the dp of some vertex is 0, then it means that no back edge is passing through that vertex, which will help vertex in connecting it to its ancestor back through its descendants. So that's why we can say that this vertex to the parent link will be a bridge. Because what was the definition of bridge? On removing that edge, the two ends of the bridge should not be connected by any other edge. And this is only possible to happen, that is, these two will only be connected if some back edge was present. But if the dp vertex is 0, that is no back edge is present, it means that this u and p will not be able to connect via any back edge, and thereby we can say that this u and p, that is this link, is a bridge. So when I will code this up, you will understand in very simple words how this will give us the correct result every time, right? So this is the alternative method to find bridge. So you can see the same thing in the blog written also. As you can see that what these three terms represent. So the number of back edges going up from u, so we are adding this, and then we also saw that we were be adding the results of all of its children because it will also be contributing to the answer, and then subtracting the number of back edges going down from u because it will not be contributing to our answer, right? So the same thing we will do in the code also. So by now I am sure that you have understood how we will find the bridges and also the subtree size for each node. We wanted to calculate the total number of elements for both of the components on each side of the bridge, right? U into V, and U represents the subtree size for the one end of the bridge, that is here this one, and similarly here V represents the subtree size for the another end of the bridge, that is this one, right? So if we maximize this, then what will happen is our answer will decrease, because at last what we want to print is this only, na? That is total number of possible pairs minus the number of pairs that we have just lost by removing the bridge. So if this term is maximized, the whole term will have been minimized. That's why we will only try to maximize this and at last subtract from the total value, which is equal to n into n minus 1 by 2, if you remember. So now I think I should write the code in the code editor and explain everything step by step of what I just told, and everything would become so clear. So let us now go to the code editor. So initially we have to take the inputs of n and m. So after taking the inputs of n and m, we have to take the inputs of m lines, and it will consist of two integers, u and v. And since it is a bidirectional one, so I will use a adjacency list in order to construct this graph, and I think I should also declare the adjacency list here only. And now what I will do is I will try to build an adjacent graph which will consist only of the span edges, right? And in the meantime we will also be calculating the bridge. For that, let me name the function as bridge dfs. We will be starting this from 1 and its parent would be -1, right? And we'll be passing this graph, and we'll also be passing other parameters later on, we will see. Since the bridge consists of two integers, so we'll be storing them in a vector pair of pair, right? So let me name it as bridge. So we will also be passing this bridge here as the parameter, And now I think I should write the function. So this will be void type only, right? And the first parameter is a node, the second one is the parent, and the third one is the adjacency list. Also be storing the result in a vector as I said, which is a pair actually. What I said, I just said that I will be visiting each one of its child of the current node, because this is how we do a DFS in a tree. I told you in the explanation that if the level of this child is 0, what does it mean? It means that it has not been yet visited. So let me declare that here as well. So vector of, so let me pass this level here like this, and initially as I told you that the level of 1 will be 1 only, so 1, and now it will be vector of int, right? This statement means that this child is getting visited for the first time, so I will set the level of this child equal to the level, whatever the level of the parent was, plus 1, right? And after that I will call the same function again, but this time the current node will be child and its parent would be node. And since I told you that we have to build an adjacency graph which will only consist of the span edges, let's name it G2, and it will also be of the size n plus 1 only, so I will pass that here as well. So here I have to write bridges and level as well, and after that G2, that I will just pass here now, G2, right? And now if you see, then what we'll do is, since we know that we are going from a node to one of its child, so it means that this node to child is a span edge, right? And we want to add this in our new G2, so I will say that G2 of this node dot push back this C, right? And similarly G2 of this child dot push back this node, because I want to build a complete tree just as the original given graph but without the back edges. I also told you that for each of the child in the DP array, I would be adding the current values of the child to the node, right? So DP of node equal to whatever the value it has already gathered plus DP of the child, right? So let me pass that DP array here also. So it will also be of the size n plus 1 only. Initially in the DP array everything is set to 0, pass it by reference as well, and also don't forget to pass. And after this, if it is not the case, so what does it mean? So if it is not the case, therefore it means that this node to C is not a span edge. So now it means that this node to C is a back edge, right? And if it is a back edge, then there are two possibilities. Either this back edge will be going from node to C in the upward direction, that is the level of C will be less as compared to the level of node, or the other way, right? Also don't forget to give this check, because this is how otherwise the link between child and parent will also be considered as the back edge, which we don't want. So if the level of the child, right, is less than the level of the node, so it means that the level of child is less, that is the back edge is going from below to upwards. So what it will do, it will contribute to the total number of DP value for the current node. So DP of this node plus plus. If it is not the case, that is if the level of C was instead greater than the level of the current node, we'll say that the DP of node minus minus. And after this has been done, I will just check if the DP of this current node is equal to 0 or not. If it is equal to 0, it means that there is no back edge that will help in connecting the U, that is the current node, to its parent via some back edge. And also don't forget to give this check that the level of this node is greater than 1. Why? Because we know that the level of 1th node is actually 1 only, and it might act as a bridge because the DP of 1 will be 0 in that case, right? So that's why giving a check, if the level of node is greater than or equal to 2 only, then only consider that node. And if it is true, then it means that the edge present between this node to its parent is indeed a bridge. So we will store that bridge in a pair. So that's why bridges dot pushback a pair, that is node and its parent P, right? This has been done, so our bridge is ready, right? And now we want to calculate the subtree size. So we will again declare a vector. Let's say subtree underscore size. It will all be also the size n plus 1 only. What I will do is I will simply write a DFS for sub, let's say I'll start it from 1 only and having a parent -1, and in this I will pass the modified graph, that is g2, the subtree size array, which will hold the final value for the subtree size for every element, right? Int node, int p, and the third parameter was g2, so then the subtree size, right? So vector int subtree size and pass it by reference. So we have saw how in the CSCS problem we have solved this, so I will do it very quickly. So I will say that the subtree size for this node is 1, and we will then visit each one of its child. C is not equal to p. I will call the same function again, but this time the node will be C and the parent will be node, and then g2 and subtree size will remain same. After this has been done, I will simply combine the result of all the children into the current node. So subtree size of the node will be the summation of the subtree size of the child, that is this. And now after doing this, our everything is ready. We just need to minimize our answer now, right? And we also know that the total value that is possible for a given graph is equal to n into n minus 1 divided by 2, right? So I will say, so this is the maximum amount of pairs that we can have in the beginning. And as I told you in the explanation that every time we would try to maximize this u into v, because that would help us in minimizing the total value after that, right? So we want to maximize this u into v. So let us say that maxi value initially is 0. Whatever the bridges we have collected, we will iterate through that. So this c dot first will be my first end point of the bridge, and this c dot second will be my second end point of the bridge. I will say that I will compare basically that in the graph whose level is up, that is which end of the bridge is present, is coming first in the DFS call, right? So I will say who up, right? And so how we will decide this who is up? So if the subtree size, right, the subtree size of this u is less than the subtree size of this v. So what does this mean? So it means that the subtree size of u is less and the subtree size of v is more, right? So if the subtree size of u is less, so it must be, so it means that in the bridge, that is u to v link, u must be the downward vertex, right? Only then the subtree size u would be less and the subtree size of v would be more in that case. So if this is true, that is if u is coming downward, then I can say the total number of elements present in the subtree size of u would be equal to subtree size of u only, right? So number of elements in u would be equal to nothing but subtree size of u only, and also the number of elements in v would be equal to nothing but the total number of elements minus this value. So this will give us the total number of elements in the other component, and we just have to maximize the product of these two, right? So I will say maxi equal to max of maxi comma number of elements in u into number of elements in v. If it is not the case, it means that u is not the vertex which is coming downward in the link of the bridge, right? So it is coming upwards. So we just have to reverse the situation. So it means that now the v is coming downward, and if v is coming downward, it means that the subtree size of v is the actual thing that we want, that is the number of elements in v. Now the total number of elements minus this subtree size of v will consist of the total subtree size of u, that is the total number of elements of u. And once we have done this, we will simply print the total value minus this maxi, right, and return. Now I think I have written the complete code, but there is one issue still, that the value of n can go up to 10 to the power 5. So that might exceed the limit of this int. So what we will do? So I think we should use long here in that case, right? So that's why long, and here also. If I run the code, let's see if it runs correctly or not. So as you can see, every test case is getting passed with this code, right? If I try to submit the same thing in the Codeforces website, let's see. Okay, so we have got a wrong answer, and I can tell you why we have got this. We have got a wrong answer because we have not used long in few of the places. Let me turn this int to long for every int, right? So now I have converted every int to long. Let's see now what happens. Okay, as you can see, the problem, the solution is accepted. So this is the code that we just wrote, and I explained you in very detail how this is working, like how why we are building an adjacent graph in order to calculate a subtree sizes, and also how we are storing the bridges by using this method described in the blog by is this fft, right? And at last we just maximize this value, and thus we got our correct answer for every test case. So I really hope you have understood the problem in very detail and correctly. So if you like the video, please subscribe the channel because it takes a lot of efforts to create each and every single video, and don't forget to like the video and share the video with your friends who need to watch this. And if you have any suggestions, feel free to write in the comment section. I will read those comments and will act on it accordingly. So yeah, thank you for watching this video. Thank you.